Well, it's nice to talk to a live audience. It's fantastic. Unification, of course, is one of the main goals of theoretical physics. And the Standard Model, of course, was a great step towards unification. One of its most outstanding features is that the content of the symmetry groups, the gauge groups that underlie the Standard Model, as well as the matter representation, from the beginning, it was realized that they naturally are crying out to be unified. They easily belong to a simple higher symmetry group, which could be spontaneously broken at low energies, SU5, SO10, E6. It didn't have to be so. It could have been the Standard Model was evidently missing something. And early attempts at unification led to quite interesting unified models, which made predictions, proton decay. But the most interesting feature, to some extent, was the fact that if you extrapolated what we know about the Standard Model, the running of the couplings, there seemed to be convergence of the strength of the forces in the Standard Model at an extremely high energy, as physics that runs logarithmically, unfortunately, as we get into the weak coupling regime. The simplest attempts to unify had couplings converging together roughly at energies of 10 to the 14 GeV, and with supersymmetry, a remarkably precise convergence at 10 to the 16 GeV. This raised the prospect of the desert, which we have been living in ever since, of a regime which perhaps no new physics would emerge until we get to extremely high energies way beyond what we can achieve in today's colliders. However, it also indicated that the unification scale, especially in supersymmetric theories, is very close to the Planck scale. And that was the reason for many of us in the 80s to turn to try to construct unified theories of the forces, all the Standard Model gauge forces together with gravity, which in any case has to be done. It's an outstanding problem for theoretical physics. As Juan remarked, that is one of the most important clues we have as to what goes on where unification might occur, and it has always been for me one of the strongest motivations for pursuing unified theories of the standard forces of nature with gravity, and in a supersymmetric fashion. And it was the motivation that led many of us to superstring theory, which is a UV completion of quantum gravity, and as was discovered in the middle 80s, can contain, upon compactification of its original formulation, 10 dimensions, all of the features that exist in the Standard Model, including chiral matter. And it gave us the dream of having a unique final theory which unified all the known forces of nature. Unique in the sense that in string theory, we have a theory in which the parameters are not arbitrary constants, but rather expectation values of fields in a vacuum, and dynamical in nature, and conceivably could all be calculated. Now, of course, those dreams haven't totally materialized for two important reasons. One is, of course, that low energy supersymmetry, which was one of the strongest motivations hasn't been seen. The reasons we expected low energy supersymmetry was that it offered a possibility of explaining the electroweak hierarchy, the mass of the Higgs, and perhaps dark matter. The LHC, we expected, would discover low energy supersymmetry. So far, it hasn't. It's still, of course, possible. Not only is it possible, there's a very large range of supersymmetric possibility, which could still yield low energy supersymmetry, and we shouldn't rule it out and continue to look for it. But there's another reason why our hopes that we could construct unified models which would give a explanation of the standard model in a sense, as well as calculate some of its uncalculable features, the mass spectrum of quarks and leptons, the couplings, et cetera, the number of colors. Why that hasn't materialized was the realization that there wasn't just one or a few consistent compactifications of the higher dimensional string theory that looked like the standard model and contained all of its successful properties, but rather there were an enormous, almost infinite possible compactifications, potential metastable vacua that could be used to construct effective field theories. And this is known as the landscape, as you know. And how could we possibly choose them? 3 minutes left. That, coupled with the cosmological constant problem, remains. Now, in the following years, there has been an enormous study of the landscape, and that continues and is extremely valuable to know what possibilities exist. It would be nice to have one of them which actually reproduced the standard model plus the cosmological constant. There have also been and continue explorations of the swampland or effective field theories that cannot be UV completed into string theory. This continues, but at present I see little hope without theoretical or experimental advance that we can achieve the original goal. A very interesting question that is beginning to be explored with bootstrap and other methods is, are there other UV completions of quantum gravity and of the standard model? We should be very open to that possibility. Just because string theory does it so successfully does not mean that there couldn't be something else. We clearly need, as theorists, as particle physicists, some indication from experiment as to what other scales and other physics lies between us and the unification scale. And many of them will be coming. Some of them we're aware of. Dark matter, observed by astronomers, certainly is an indication of new physics. The neutrino mass scale, precision experiments show some hope for discovering new physics. All of that, I think, is going to be crucial to be able to construct not just in principle unified models, but predict unified theories that can be predictive. On the other hand, what we also need is the much greater understanding as to what is string theory at the more formal level. In fact, what is string theory is the name of a KITP program we'll be running in a year or so. We face the problem, whether we believe in the landscape as the end of the ability to make predictions. We need to answer the question as to, in string theory, what picks the correct theory, the correct vacuum. That could be the landscape, anthropic arguments, could be the answer, but we're far from having control over the dynamics of that. And internal inflation, how are different vacua populated? And in my opinion, the most important question there is to understand the initial state of the universe, important for cosmology, as we just heard as well, but in a theory that unifies the ordinary forces of nature together with gravity, the solution is a space-time history, and that must include the beginning, perhaps the end. Finally, there is one aspect of string theory which is certain to be valid, and that is the QCD string, which gave origin to string theory, and which, with modern techniques, I believe is ready for a much greater understanding. We have evidence from experiment, wireless gauge theory, if you want, and from ADS-CFT that mesons in QCD can be described by some kind of string. And we have many new tools to try to understand the QCD string. That will be very useful because it connects directly to experiment, quark-gluon plasma, the new experiments which will exist at the electron-ion collider, the discovery and further discoveries of exotic QCD states. So I think we are in a position at this point to understand in detail and in a quantitative sense the nature of confinement and the string theory description of QCD states. And that should also, aside from the wonderful phenomenology of hadrons, give us a good control over a real string that exists and that we can explore experimentally and is non-supersymmetric. Okay.
Thank you. Thank you very much for another beautifully sweeping talk without visual aid, no less. Are there any, Csaba?
You started the discussion of unification by saying that the standard model particles naturally fit into multiplets, but that's not quite true for the Higgs boson. Yes. So I'm wondering if you think whether that has any significance, or is there any message there, or?
Well, the Higgs, is not beautiful. It's ad hoc. We need it, and it's the simplest solution to understand electroweak symmetry breaking. I didn't have to. There's no question that one of the major goals of experimental high energy physics should be to explore the Higgs sector, since it's so ad hoc.
I just meant the fact that it doesn't have a partner.
Right. Right. No, the Higgs, well, in unified models, as you know, we simply add Higgs as needed. In string theory, of course, Higgs are there dynamically. They're part of a bigger unified theory. But you're right that Higgs plus the gauge theories is not unified. String theory does unify them.
I would thank you.
But remember, the initial attempts at unification occurred long before the Higgs was discovered, and it was
so we are into our
Good question.
break time. We can, okay.
Michael Peskin.
Michael.
So David, you and Juan both talked about this unification of couplings as kind of a lodestar that we should think about in trying to think about unification. This is always, I guess when I started to learn about this, it made me a little uncomfortable for the following reason. If you assume that it's the standard model until 100 GeV, and then it suddenly transfers to the supersymmetric spectrum, and you do everything at the leading order, you get exactly the right unification, just bang on. Everything you do to improve that picture makes the picture worse. And now that we have to move the SUSY scale to multi-TeV, as indicated by the fact that the gluino doesn't seem to appear at the LHC, a lot of that evolution does occur when alpha S is as strong as it gets. Now, it's all in the region where this could be, you could repair the discrepancy at the high scale with threshold corrections there. But still, I think there is room for doubt. And probably it's worth emphasizing that to this group.
Yeah, no, of course, it's really two lines always meet at a point. Three lines to meet at a point is one coincidence or prediction or clue. And so it could be a coincidence. What is not a coincidence, however, is that those three lines more or less meet. It was already evident from the non-supersymmetric theory, more or less meet at an energy scale close to the Planck scale. So that, for me, was always enough to believe that unification of the ordinary gauge forces cannot be divorced from seeking a theory that contains quantum gravity.
Let's thank David again. I think that we have lots of interesting things to discuss during the break. We will come back at 11:15. Let's thank all the speakers, Tauhan,